Hi. So, after the last lecture, today what we will be doing is we will be reviewing a few more examples of CUDA program writing in terms of we will start with simple CPU only programs and also show that how the corresponding CUDA variant of the program which will run on a GPU can be written. Now, we will have some very simple examples. For example, we will start with a basic matrix multiplication program. So first we consider only the CPU only code. So this is a basic matrix multiplication kernel which is designed to run in a CPU. Let's see how it works. As we know that any standard matrix multiplication should have 3-level nesting of loops. So we have a outer loop which is essentially iterating over this I 0 to n, and we have this inner loop j 0 to n. So basically I am using this I and j to select the ith row and the of matrix M, and I am also using the inner iterator j to select a specific column, and in that way once for every possible choice of I and j, the inner loop carries out the computation of the ijth value of the result matrix. That is the essence of any matrix multiplication program that we know is standard for any CPU only case. So essentially we have this outer two loops selecting the I and j, and inside this inner loop we carry on this computation of the ijth entry of the output matrix. As we can see that inside this loop what is going on, we are kind of traversing the ith row of the M matrix, and we are traversing the jth column of the n matrix. We are performing pointwise multiplication followed by addition, and that result gets accumulated in the variable p value, which is written back to the Pij matrix which is storing the result. So that's how a standard CPU only code works, and we like to see that what will be a CUDA variant of this code. So for CUDA variant, as we know that there has to be a host program and a device program. So this is how the main will look like. So you will have a CUDA memcopy, because of course we need to remember that we need to send the input matrices M and N to the GPU side for doing the matrix multiplication, right? So we execute these commands CUDA memcopy, and you use them to send the matrix M as well as the matrix N to the GPU. Once this is done, we define suitable grids and blocks here. As you can see, they are given some specific numbers here. So essentially we are defining a 2-dimensional grid, and this is denoted by this 2, 2, 1. So we have a 2-dimensional grid. In each dimension I have the dimensionality value of 2. So in that way I am having 4 thread blocks that are getting defined, and then inside each thread block I have 64 threads that's getting defined by this definition of block 8, 8, 1. So inside each thread block I have 64 threads, and they are also arranged in a 2-dimensional pattern, right? So with this configuration of grids and blocks that's defining the arrangement of threads for the program, we are firing the matrix multiplication kernel. So this is the code that is going to execute on the GPU, and it is assuming that it has got the matrices M and N available to it from the inside GPU's DRAM, and that's already available due to these CUDA memcopies that have already executed. Once this kernel executes, I am expecting that the result should be available in another part of the GPU device memory, that is DP, and I will be using this CUDA memcopy command again to copy back from device to host these values from the location DP to the original target product location P in the CPU in the CPU's corresponding DRAM. Let's just have a small look at the basic matrix multiplication kernel. Essentially, is very simple code. So it's going to execute this part of the code sequentially in a per thread basis. The kernel has been launched with this many number of threads. The threads are arranged in the grid comma block pattern as has been discussed. So if I ask what is the total number of threads that have been launched, that would be, let's just work it out. So it would simply be this 2 cross 2 cross 8 cross 8. So that would give me 64 cross 4. That's the number of threads that are getting launched here. So for each of these threads, the thread ID and the block ID variables will get their own specific values here, as we have learned earlier also. So for example, the first thread should have a block ID 0 and thread ID 0 here, and so in that way I can use those values to compute an I and a j. So this essentially is giving me what is the index for which I am going to do the computation. Now let's try to map this properly. So what do we really have? For I have got one thread. That thread has a specific block ID and a specific thread ID, right? So if I do a block ID x dot y times block dimension dot y plus thread ID x dot y, then I get an I value, and this I value is denoting a row of the matrix, the operand matrix 1, that is M, or here the device side is DM. And similarly, if I do a computation of this j, what do I really get here? So I have a block ID x value, and I am multiplying it with the corresponding block dimension, and I am adding it up with the thread ID x value, and this gives me a corresponding column position in the other matrix on the device memory, and that would be Dn. So if we take this pictorial example, and this gives me the more holistic view of the system. So now have a look at the original code here. So you have defined a grid containing 4 thread blocks, right? And you have, for each thread block, you have got a block of 8 cross 8 size. That means you have got 64 threads executing. So this is how it's going to be arranged. So you have this many number of threads that have been launched. Each thread is trying to compute one of the elements of the target matrix, right? Question is, how will each thread know for which value it is going to do the compute? This is the main problem here. Now as you can see that we have 4 blocks due to this grid definition of 2, 2, 1. Each of the blocks are getting marked here in different colors. These 4 different colors I have, and for inside each of the blocks I am going to have these 64 threads as per the block definition we have discussed earlier. Now suppose I pick up any one of those threads. Let's say the thread has got this point. I am talking about the thread at this point, which is highlighted here. So if I just ask what is the block ID of this thread, so it's easy to see that the blocks, since the blocks are dimensioned from 0, so I have block IDs of these 4 blocks as 0, 0, 0, 1, 1, 0, 1, 1, right? So I would have for this thread the block ID x dot x as well as block ID x dot y values both as 1, right? Now suppose I am trying to get back from this block ID x and thread ID x values what is the corresponding row and column position here in this target matrix for which the thread is going to do the computation. Now this is what is getting done here, right? So let's break it and observe it here. So I have already understood that how I can get the block ID x dot x and block ID x dot y values. Now what about the values of the thread idx.x and thread idx.y values for this specific thread? So as we can see that here we are looking at the fourth row. So 0, 1, 2, 3. So thread idx dot x, if I say that what is the thread idx dot y, so that should be 3, and what is the thread idx dot x, so that is this much, right? So that's 0, 1, 2, 3, 4. So that should be 4, right? So in that way, looking back, for that thread ID, I can compute what is the thread idx dot y value and thread idx dot x value. I mean, these are the values that the thread has already got, and it has got to use these values to compute the I and j. So that's like a motivation of why this expression is there. But the issue is we have to compute the value, right? So the value of the row is I and the value of the column is j. So I would essentially mean this height, there is a row, and j would essentially mean this shift, there is a column, right? The height I would be now getting by following this formula. So we have to look at what is the block ID. If I am talking about I, so essentially I am thinking in terms of what is the block ID y. That block ID y needs to be multiplied by the dimension of the block. So since this is block ID 1 and there was already a block here, so you multiply it by the block dimension, so you shift this much. That's why you have block idx dot y times block dimension dot y, right? And then you are trying to figure out what is the shift in the y axis further inside this block, right? Now that shift is, as we know, 0, 1, 2, 3. So that's the value of the thread idx dot y variable. So that's why for computing the I, we will have to write this block idx dot y times the block dimension dot y all in the y dimension, and we have to add the shift, that is the thread idx dot y value. So this gives me the value of the row, the target row for which I am going to do the computation. Now similarly, I can do a computation of the value of the x, right? So sorry, the value of the j. For I have j. Now j represents, I mean, what is the column index for which I am going to do the computation. But how do I get the j? Now in terms of xy axis, as I can see that j should correspond to the x dimension of the blocks as well as the threads. Since the block idx dot x is 1 for this block, so that means I would multiply it with the block dimension. So that's what I do, right? So block idx dot x times block dimension dot x, and I would like to add to it the thread idx dot x, right? So that's what I have, plus the thread idx dot x. So then in that way, using these values of block idx dot x, block idx dot y, thread idx dot x and thread idx dot y, I have been able to compute the I and j, and that tells me what is the target location for which I am going to do the matrix multiplication operation. After being able to recover this I and j value from the values of the system variables in terms of threads and blocks, the kernel will proceed into this loop. It has a loop which is iterating from k equal to 0 to n. Inside this, essentially this thread would be traversing this row for matrix dm in the device memory, and it will be traversing this column. So I mean, we are sorry, so this picture should be actually, I mean, reverse, like this, the row should come on this side and this column should come on this side. So essentially you will be multiplying them to get the value here, right? So just consider this one on this side and the column matrix on the opposite side of this. So anyway, so looking at that, the question is what should be the expression here? As you can see that the expression would nicely match. So for every value of k, all you are doing is for a fixed row, that is the ith row, you have got I times n. So you have already covered all the other elements preceding to this row, and then you shift by k, right? So when I am talking about this entity, I am referring to this matrix. Think this is on the left hand side, right? So I will do I times n. N is the x as well as the y dimension of the matrix, and you shift by k positions to get to any of the k positions here, and you are multiplying it with the this columns corresponding value. So that's why you are also thinking that okay, essentially you are doing a computation of the ikth element times the kjth element. So the ikth element from this matrix is getting multiplied by the kjth element of this matrix, right? So in that way you multiply the contents of this row point wise with the contents of this column again point wise, and you are accumulating that sum, and that sum goes to this position. Now of course, why do we do this multiply by n? Because as we know, following C and other programming languages, that I mean this is the way we always do, for the simple reason that the arrays would be stored in the memory sequentially. So coming back to the code, for every thread, the first thing that the kernel has to do is find out what is the location in the memory for which this kernel is supposed to do the matrix multiplication computation. That means you are given a kernel. When you have launched the kernel, you have launched that many threads, you have launched the number of threads as is the size of the 2D matrix, right? Now, so one thread is going to be responsible for doing a computation of each location in the matrix, but it has to figure out what is the location. For that, what it does is it recovers the I and j value. The way it does is it has a loop into the block IDX, thread IDX values corresponding to the thread, and it tries to figure out what should be the I and what should be the j. Using this I and j values, it is going to find out, okay, in that case, I am picking up this row from the matrix M and this column from the matrix N, and it does the pointwise multiplication and accumulate. Once this is done, the value is stored in this variable p value, and it's read back. So the question is, all that is going on is, for the GPU case, the computation is done in a per thread basis. The possibly problematic scenario here is you have to identify that how to map the computation in terms of the thread IDs and block IDs. So like you are firing the kernel with a suitable launch parameter set that is specifying how the threads are going to be arranged hierarchically, and then you are using these launch parameters to identify your working set per thread. In this case, the working set for this thread is this location ij, and we have already explained how to compute the value of I and j from the block IDs and thread IDs, and you are going to use them for doing the computation here. So in that way, you have the matrix multiplication operation done. Now one thing has to be remembered, that this is not an optimized GPU program. Why I say that this is not an optimized GPU program, we will learn later in the course, where we show that how this matrix multiplication computation can be accelerated by using several primitives that GPUs additionally offer to you. Here all we are trying to do is we are trying to parallelize the program. We are simply saying that this operation of matrix multiplication has got lot of parallelism, because I can compute each of the ijth element of the product matrix independently. There are no conflicting writes that are going to happen in the product matrix space. Due to this reason, I can launch a GPU kernel having as many threads as is the size of the matrix, so that each thread is responsible for computing one element of the product matrix, and the way it does is, as we have already discussed, that it will recover the working set and then it will decide how to do the computation. And so every thread is executing this sequence of code completely sequentially, and when this kernel is completed, we would have got the result available in the GPU memory, and from the GPU memory the data has to be copied back to the CPU memory by using this CUDA memcopy command. So that would be our way of doing the matrix multiplication computation. So with this we'll complete this simple example on matrix multiplication, and thank you for your attention, and in next we'll go through another a bit more involved example, and this will be part of our coverage of basic CUDA programs without much of optimizations. Thank you.